It is my pleasure to introduce Raghu from NEC. He will be leading this short course. He has expertise in quantum computing and high performance computing. And he's going to be giving you an introduction to NEC's simulated annealing, or otherwise known as vector annealing. Welcome. Thank you.
Thank you very much, Lisa, for the introduction and the opportunity to present NEC's product and the solution for a very unique problem. So thank you for inviting me. As Lisa mentioned, my name is Raghunandan Mathur, and I belong to NEC Corporation with an experience in HPC optimization and quantum computing. What we are presenting here today is NEC's unique solution that that solves some NP hard problems using quantum annealing techniques on NEC's HPC hardware, which is known as the vector engine. So it's a hardware and software solution combined together, and we call it vector annealing. And I appreciate everybody giving your time today. And since my screen is shared, I will proceed with the slides. This is the first of its kind at Texas A&M, and I'm sure some of you may have experienced or you may have experience of working on annealing solutions, but at the same time, there must be people who have little to no experience of working on these technologies. So please feel free to ask any questions, stop me. And I think because I will be focused on the slides, I may miss some messages on the chat. So it would be fine if you guys just unmute yourselves and just ask your questions so that the session is more interactive. There is some theoretical information on these slides, but there's also some hands-on. If you have a pen and paper, that will help some of the slides. But at the same time, we will go through how we can run these codes. And I'm sure you guys have your access IDs, and I will take you through those things as we proceed. So before we begin, there are some basic steps and some information. The slides that I'm presenting are already available on your ACES cluster, your user accounts. The path has been provided. The hands-on source codes that we will be running are also available. So what we can do right now is just log on to our Texas A&M portal. I hope the portal is visible on my screen.
Yes, we can see it.
Thank you. Okay, so everybody, you have to go to portal-aces.hprc.tamu.edu. And after logging in through your access IDs, you will see a screen like this. Okay, once we're logged in, we will go to clusters and get this shell. Clicking on that link will take us to the login node that's called the A login node. And yeah, for everybody else who has been able to log in, we will just make an SSH to a different node that's called DSS. That is where the solution has been installed. So all you have to do is SSH DSS, and that will take you to the DSS node. This is where we are gonna work on everything that's mentioned on that slide. The next thing that we have to do is type source VA setup. So Lisa has very kindly created this script, which involves all the packages and environment variables that need to be installed. So this single command can allow you to invoke the vector annealing environment, which we will later use. But I just want everybody to set it up now, and if there are any troubles, maybe while we proceed, people can receive the troubleshooting. So as soon as you enter source VA setup, you'll see that VA is uh, prefixed before your prompt, and that's an indication for everybody to uh, make sure that the VA environment is loaded. If everyone has been able to reach till this point, we can consider their environment as set up. And the only thing you may have to do is copy the codes. So you can use the CP command that's provided here. There is a directory by the name VA demo codes, and you can copy it into your user directory. So I would go to my user directory on Scratch, if you can copy exactly what I'm doing here, except for my username. Please ignore everything that's here. I will just run the same command. Scratch training NEC VA, and you'll see VA demo codes here. And you can copy it to your current directory. You will see 3 directories here: Sudoku, LLRO, and TSP. And we will stop here and proceed with the slides. Okay. So how do we start? Let's start with the fundamentals of quantum mechanics. What this course is about is we are using some techniques that are provided under the umbrella of quantum mechanics, and we will utilize those techniques to solve problems which are very difficult to solve on classical computers. So what exactly is quantum mechanics? We can say that it's a theoretical framework that describes the behavior of matter and energy at the quantum level. By quantum, we mean subatomic, at a under the hood inside the atom at a particle level. The greatest thing about the quantum mechanics is that it challenges classical intuitions. So if I were to say that if I had a ball in my hand, and if I chose any one of you and I threw the ball towards you, your notions and intuitions of physics and your experiences will probably lead you to catch that ball, because as soon as the ball leaves my hand, you will have an intuition of how the trajectory of the ball towards you will be, and you will have an intuition to be able to catch it. Now, if we imagine that if we shrink ourselves down to the subatomic quantum level, and there I try to throw this quantum ball towards you, it will challenge your classical intuitions, because there may be some very interesting behavior that the ball, or at that level, that particle will exhibit, and it may not follow the same trajectory. You might be able to see it vanish from one point and appear at another point, and various different uh, uh, your intuition will be challenged in that way. And that's the most interesting thing that's happening at the quantum level. Uh, it also introduces concepts like superposition and entanglement. There are many more things, but these are two very crucial things that we have to understand when it comes to quantum computing. And like I said, it introduces probabilistic behavior at the microscopic level, fundamentally altering our understanding of physical phenomena. So what's essentially happening here, or what essentially quantum mechanics is doing is, which we are able to leverage in quantum computing, is that when we are able to store a bit onto an element, what we do in quantum mechanics is we work with quantum bits. And I will explain to you how that works in the forthcoming slides. On the right, you can see a little animation which might help you understand how we will be dealing with these problems. So on the top, you can see how things work in the classical world. It's a maze that you're trying to solve. And this maze obviously has various combinations where you enter at this point, where my pointer is, and exit at this point. So you're seeing that in the classical world, you will traverse every path, hit a dead end, and retrack your steps to find which path will actually eventually work. And the dark circles that you see here are basically the traversed paths which ended up in a dead end, and you had to walk them again until you finally reached the exit. So you can see how this involves a lot of combinations of various paths. You have to traverse each path, hit the failure, and then retry those paths until you hit the final result. But in the quantum world, you are able to just traverse all paths together instantaneously and eventually find the exit path. And so it's not exactly a iterative process where you're going through every possible path just to ensure which one was the most optimal or which one was the most correct. So this is the analogy which we will use further in this lecture to understand how quantum annealing works. So I just introduced the idea of quantum computing. So this is basically a difference of how we are using quantum mechanics into quantum computing. So we know in our classical world that everything, the building block of the classical computers is regular bits. And for quantum, the building blocks are qubits. What we know about regular bits is they can either be 0 or 1. And the thing about with qubits is that at the quantum level, the particles are able to exhibit this special feature where each bit can not only just store 0 or 1, but they can represent various various states in which could be a combination of both 0 and 1. So this provides quantum computers uh, this power to store more information within one bit representative. So to imagine this, you can think of a magical coin where a regular coin can either be heads or tails, but a quantum coin, you can imagine it to just be in the air, and it can be both head and tails till the point you catch it. So the normal state of a qubit is similar to that of a spinning coin, where it is both head and tails at the same time. This is an analogy. So the concept of superposition is also understood this way, that when you look at a qubit, then you can see that they are able to exist in multiple states. They could be percentages of 0 and 1, and these can be variable, and there are ways to measure it, but they are probabilistic. So one specific qubit can have various states between 0 and 1, that there are uh, parts of 0 and 1 both within the qubit. And another extremely interesting concept for a qubit is entanglement, where qubits have been found to be naturally entangled with each other, such that one qubit, the state of one qubit can be understood as connected with the state of a second qubit. So if you were to take an analogy again, it's like you have two boxes, and if you open one box, it has a glove that goes onto your left hand, and the entanglement will prove that the second box that you have, when you open it, it will have a glove for the right hand. So there is a connection. So if a state is, let's say, in the one state, or let's say 15 to 85 of 0 and 1, then the entangled qubit will probably be in the same state or the exact opposite state. It will be very dependent. So as soon as you change the state of this, you'll identify that the state of the other qubit is also changed because of the entanglement between these two. So while quantum mechanics can be vast, and the brightest minds on Earth are still working on understanding these concepts, I just wanted to introduce these basic ideas which we might find relevant in the lecture ahead. So let's talk about what a combinatorial optimization problem is. And the idea of combinatorial optimization problem comes from the fact that we are using quantum annealing to solve combinatorial optimization problems today. So in this situation, it's very easy to understand what a combinatorial optimization problem is if we break it down into what a combinatorial problem is and what an optimization problem is. So let's just see, as the name suggests, it has to do with a number of combinations to the solution. As we saw a maze in the first slide, that could be one idea or one analogy. So you can understand that a combinatorial problem is characterized by its inputs, which is an objective. So, for example, I have to go from point A to point B, and I want to do it with minimum cost. That is my objective, that I can traverse from A to B, and the cost should be the least. Then any conditions like the preferred mode of transport, is it a train, is it a car, preferred time of the day, do you want to go in the morning, do you want to go in the evening, or maybe like a flat tire, or traffic jams. These are all conditions and parameters to achieving that objective. Like, I may face these challenges from going from point A to point B. So what path should I choose? What time of the day should I choose, or what mode should I choose? All of these are combinations that will help me resolve my objective. So you can solve a combinatorial problem by finding a group of discrete, finite set of objectives that satisfy the conditions and eventually help you meet the objective. So if all the objectives are achieved, but if the objective is achieved, but all conditions are not met, for example, in my example, I was able to reach point B from point A, but because of a flat tire, I had a delay there. So in that case, it was eventually a solution. You can call it a candidate solution because it helped you eventually to reach point B. But if I was able to meet all the criteria and satisfy all given conditions, I will say that was my optimal solution, because I was able to reach point A to point B by avoiding any delays and doing it at the least cost. In that case, we would call it the optimal solution. So combinatorial optimization problem is where you are trying to optimize the combination, the combinatorial problem. And how do you see an optimization problem? What we called an objective in our previous explanation, you can just represent it as a mathematical function. So in my example, we can say that I will create a function, and I will convert it to a minimization or a maximization problem mathematically. So if I am able to minimize the function, then I will say that I was able to find a solution with optimal quality. And then there are variants of optimization problems where you are finding a solution with optimal objective function value for a given problem instance. That's called a search variant. Or if you're determining optimal objective function, the value of it for that given problem instant, and we call it an evaluation variant. So when I say a function, let's imagine this black curve that we see here. That is the entire solution landscape for that mathematical function. And you will see that there are some local optimas where basically the troughs where everything goes to a minimum before before moving on to being uh, the most optimal solution, and that would be where the entire curve hit its lowest energy. So the goal is to find an optimal solution from a finite set of solutions. That was always the goal. There are multiple local minimas where the solution achieves an energy where you can consider it as an optimal solution, but there is the most optimal solution will be the one where your uh, curve is at its most, you know, at the minima. So the challenge here is the solution space. It might be too large. Like if I say, how can I go from point A to point B? And there might be multiple routes to that. And we actually have this on our day-to-day basis through Google Maps. But it might be very difficult to explore the entire solution space exhaustively using brute force. So in this case, I've already given you the example of shortest or cheapest round trips, but there are so many more examples where you have your planning, your scheduling, and large companies have to deal with supply chain optimization. There are continents involved where you're supplying parts and there is a demand in a specific region. How do you make sure that a large portion or large chunk of the stock is available where the demand is the most? And in laboratories, you can see similar problems with circuit design. What's the most optimal route? What's the most optimal circuit? In drug discovery, we see protein structure predictions. So all of these problems, when you plot them onto a mathematical function, you will see that the space would be so large that it would be very difficult for a classical computer to solve those problems through brute force. So what do we do in this case? We use quantum annealing, you know, because the fundamental rule of physics is that everything tends to seek a minimum energy state. So you know that hot things, they cool down over time. If you put an object on top of a hill, it will roll down. So this behavior is also true in the world of quantum physics. So quantum annealing simply uses the concepts of quantum physics to find a low energy state of a problem, and therefore the optimal or near optimal combination of elements for that problem. So in the current context, if the solution space that's here, it's taken up as the energy landscape of a quantum system, we can find the optimal solutions naturally. So I will explain this in more detail. And the idea of simulating this quantum annealing process by a meta-heuristic approach on a classical computer is called simulated annealing. And in this context, we are using vector engine accelerators to do that. Great. So we talk about annealing. What exactly is annealing? The dictionary meaning or the word annealing basically comes from the process of metallurgy, where when you're forging swords, you basically take a material to a level of uh, you know, critical temperatures, which result in structural or property changes. So you know how when you're heating a metal, it goes red hot, and then you do something to it and you let it cool down so that it retains the change. So this is the concept of annealing from metallurgy, and that is also what we are using at the quantum level. It's an analogy, but it works exactly how it is. So simulated annealing is a probabilistic meta-heuristic technique inspired from this process to solve combinatorial optimization problems or optimization problems where you design a function and you let physics bring it to a level of entropy, because it naturally will have the tendency to find local minima. And whichever solution has the least amount of energy is considered the most optimal. So eventually the goal is to achieve minimum energy or temperature that results in high probability of success of achieving a speedy as well as accurate solution. So you see that this wing of quantum computing is more natural, and we are relying on physics to provide us with the optimal solution. And it's very different from the kind of programming that we have learned in the classical realm. Um, so how does this take place? The first step is initialization. So at the start of the quantum annealing process, you see that the qubits we spoke about are initialized in a way that represents the problem at hand. These qubits are like bits in classical computing, but with the added magic of quantum superposition and entanglement that we spoke about. So that's the first step. You have to initialize those qubits in a way that will help you solve your problem. And then the system is subjected to an annealing schedule, and it basically defines how the system transitions from an initial state to a final state over time. And during this evolution, the qubits explore various configurations. They seek the state that corresponds to the solution of the problem. So this is the most interesting part, where as a programmer or as a user, your job is to just initialize things in a way that help you, and eventually the annealing schedule will help the system achieve a state that will correspond to the solution of your problem. And as we spoke about objective functions earlier, the central to quantum annealing is the concept of an objective function. And the function encodes the problem we want to solve and is translated into the quantum system's energy landscape. And finally, the goal would be to configure the qubits that minimize energy, and the minimized energy will represent the optimal solution to the problem. And finally, the system actually settles into a state, and at that point, the configuration of qubits, it will correspond to the solution. So this is how we can imagine the process of annealing. So in the quantum world, um, you can denote a variable as 0 or 1, as we spoke, but at the same time, you can also denote it as a magnetic spin, because we deal with ions. Um, the particles can be considered as ions, and we can consider them as a spin up or a spin down, which are a very similar analogy as zeros and ones. It only talks about what state the qubit is in. And this is an example where we show how large simple problems can get. So on this slide, you can see if there is a system with 3 variables, it is necessary to perform 2 to the power 3 or 8 calculations. So on the right, there are possible combinations of the spins, followed by a representative energy for that combination. Now, like we don't have, these are just representative numbers here. So you can also imagine this as a truth table where you have 0, 0, 0, 0, 1, 1, 1, 1. So it's like spin up, spin up, spin up, spin up, spin down, spin down. So that these are all the 8 combinations of the 3 variables that we're working on. And if you map these spins with zeros on, you're basically looking at a truth table. If the number of spins is 3, it is possible to perform a full search. What we are able to see here, it's not a big deal because it's just 8 possible combinations. But as you try and increase this 3 to, let's say, 10, you will immediately see that from 8, the landscape has increased from 8 to 1024. With 20 variables in the picture, it becomes close to approximately 1 million. With 30 spins, it's 1 billion. And if there were about 1,000 spins that a problem is dealing with, you can see that the combination is so large that it's almost impossible for a classical computer to solve it. And as you can see, each spin is actually representative of a combination. So it's very easy to get a problem that may require 1,000 spins. So this is why we have considered these problems unsolvable in the past with classical computers. But with technologies like quantum annealing coming forth, we see more and more of these solutions being possible to be solved. To solve these problems, because we introduced the idea of magnetic spins on this slide, let's talk a little more about how these spins are represented. So Dr. Ising is basically the scientist on which on whose name this model is represented. It's a very simplified model to calculate the direction of spin of atoms for composing a crystal. That was the contribution of Dr. Ising. And the Ising model is basically a very simplified representation of the behavior of magnetic materials. And this is the energy, the equation of energy of the entire model. So in this, the sigma represents Ising spin, the J represents the interaction coefficient between spins I and J. So which means whether the two spins want to point in the same direction or opposite direction. And H is the bias or the magnetic field on the specific spin. So these three variables collectively form the Ising model, and it is written in the form of a Hamiltonian equation. And Hamiltonian equation is what is required when it comes to preparing your objective function for annealing. So on this slide, the message is that when we spoke about writing an objective function, we have to write it in a way that a quantum annealer understands. And a quantum annealer understands when you formulate your problem as a Hamiltonian. And we will utilize the power of Ising model to represent what we can speak in English into a Hamiltonian, which is understood by a quantum annealer device. Which brings us to QUBO. QUBO stands for Quadratic Unconstrained Binary Optimization Format. It is basically a framework which is used in quantum computing, and it involves representing the optimization problems using binary variables. So you can see the binary aspect here, and it is particularly suitable for combinatorial optimization problems. So you can see if you break this down, you will see that it is a format for optimization. It requires binary variables. It should be in a quadratic format, and there should be no constraints added to the equation yet. As we can recall that our problem was an objective function with constraints together to solve the problem. So the idea of unconstrained is you represent your problem as a QUBO while the constraints are not yet taken care of. So it's basically how you express your problem for the quantum computer to efficiently tackle. Now, in this case, I've taken an example. Let's say you have 3 tasks and you have to solve this problem using quantum annealing. So each task can either be done or not done. And you want to maximize the total value, where the value of each task is as follows. If you do task A, you get 3 points. If you do task B, you get 5 points. If you do task C, you get 2 points. Now, your problem is to find a combination of which tasks should to be done or not done. So you assign a spin to them, but eventually your objective is to have the maximum value. So we introduce 3 binary variables, xa, xb, and xc, where each of these can be either 0 or 1. And the objective function just becomes an equation where you take 3 times xa plus 5 times xb plus 2 times xc. Now you can see if all 3 tasks were done, this would be 1, 1, and 1, and you would find the largest number, which would be 3 plus 5 plus 2, that's 10. And if any of these tasks was not done, you would find, let's say B was not done, so 5 would be multiplied by 0. So you would have 3 plus 0 plus 2, which is still 5. So you're able to have various combinations of A, B, and C, but the objective is to have the maximum total value. So this is a simple example of how you would want to convert your problem from English or spoken language to an objective function in a QUBO format. Awesome. Great. So time for our first hands-on exercise. Lots of theory. Okay, so you can see a problem on the page. Very similar to what we discussed. There are three tasks, A, B, and C. They can either be done or not done. And now you have to maximize the total value. What would be the cubo here? Let's say 30 seconds. Okay, we have an answer, which is correct. Great. So we're getting the drift here. I understand it was a very close problem to the one that we discussed. So we can move to another one. Now, it's again very similar. Oops. Yes, we can do a quadratic example. This one's very similar. Now, we change it. We change the language here, and we say now represent the following constraint using binary variables. Now, the constraint is at most out of three tasks, X, Y, and Z can be selected simultaneously. Sorry, at most two out of three tasks. So there are three tasks, but now you have to write something where one of the tasks should be rejected. So at most only two out of the three can be selected. Okay, so let's see how this works. It's slightly complicated. Now here we see that the terms xx, xy, and xz, they represent if the task is being selected. So if it's selected, then this is 1. If it's not selected, this is 0. And then the terms enforce the constraint that at most two out of the three tasks can be selected simultaneously. So in this case, if you see, if let's say all three were selected, then this would be 1 plus 1 plus 1 minus 2 minus 2 minus 2. And if at least two were selected, then you would make sure that one of these were eliminated. So this would be a 0 only when two of these tasks are selected. Let's write a cubo for a traveling salesman problem. Now there is a traveling salesman problem, and you have 4 cities. The distances between each city is between A and B, the distance is 2. Between A and C, the distance is 5 and 3 and 4 and 6. And you have to make sure that the total distance traveled is the least possible. Is it possible to write a cubo for that? Okay. So the answer here is we multiply the distance between each city, where each term represents the distance between the two cities multiplied by the corresponding binary variables indicating the visitation of those cities. So someone went from A to B and B to A, and you multiplied it with the distance. So XAB here is 1 if the route goes from A to B, but 0 otherwise. So this will provide you, this is a cubo representation that helps minimize the total distance traveled.
Oh, excuse me, I had one question. Sorry, I joined a bit late. Maybe I missed this. So when you were minimizing the E of X for the traveling salesman problem, what we are trying to achieve is a binary vector which would represent all these XAB, XB, and stuff like that, such that E of X is minimized. Am I correct?
Correct. Yes, that is the
I
intent.
see. I see. So just to maybe extend it a bit further, if instead of having a undirected graph, I say had a directed graph in which the distance AB was from A to B and the distance B to A might be different. So I could have just said XAB plus XAB times the distance A to B plus XBA times the distance B to A. That's effectively what I'm doing in this expression as well, right? If I'm not wrong.
Yes, you're right. If you said that B to A is a different distance, then yes, XA
Yes,
plus the distance times XBA. Correct. You have the right understanding.
I see. Thank you.
And it's always in the objective. So yes, we are trying to minimize E of X. And that's also because that was the problem. A traveling salesman problem is usually about minimizing the distance. It may have been a different nature where we were maximizing it, but yeah, this would be the representation of that objective.
And just one more question, just I'm trying to comprehend what this expression is trying to say. So the way I see this is that, so let's consider the first term, which is twice of XAB times XBA. So this
Mhm.
term would only be considered if I go from A to B and again take the same edge back. Am I right? Because otherwise I would have at least one of these binary variables to be zero. Is that correct?
It is correct, yes.
So what I don't understand is how this minimizing E of X will actually minimize the total distance traveled, because E of X is not representing the total distance traveled, right? Because I could go from A to B, then B to C, and then come back from C to A. In that case, I would effectively just get zero, because in none of these expressions I would have traveled the edge both ways.
That is right. So if you're doing, let's say, A to B, and then you're
Yes,
doing B to C, in that
yes,
in that case, the B to C aspect would be 1, and,
right?
and your A to C would be 0.
Yes.
So this is how you're able to cover that aspect of it. Because
So
it, Mhm,
So I'm sorry to interrupt you, just one question. So if
mhm.
I suppose let's take a simple tour. From A I go to B, B I go to C, and C I go to D, right? So basically I'm visiting the edges in the order A, B, C, D. So in
Yes.
that case, XAB would be 1, but XBA would be 0. The first term which I have in EX would be 0, right? Because the second variable is 0, so that term goes away. Then similarly, the second term of this expression would also be 0, because I never really go from A to C, and
Mhm.
neither I go from C to A. And the third term would also be 0, because there is no connection between A to D and D to A, because from A I only ever go to B.
Correct.
Then B, now only this a fourth, now even the fourth term would be 0, because I'm going from B to C, but I'm never going from C to B, right? And similarly, the next term and the, like, effectively every term in this expression would be 0. So
Mhm.
I mean, the way I see this is like, at least to me, it seems like I might be overcounting in this case. I might be picking up paths which would give me E of X is equal to 0, which might not actually be the minimal paths. So
Right. But okay, actually there is a constraint here that each city needs to be visited only once.
yes,
So I think, yeah, maybe this should have been an OR operation. Like
yes, exactly. It should be a plus there.
Okay, thanks for spotting that. Yeah, this is a plus.
Yeah, yeah, exactly. That was my question. Yeah,
Okay, good. Thanks for pointing that out. I
yeah,
will fix it. I will fix this in the
yeah.
some more on this. So now in this case, we are working with spin values, and now we've brought the icing aspect to the cubo again. So what we are able to do is, when we say that spin values are expressed as 1 and -1 in the icing format, you can say that the spin values are expressed as 0 and 1 in the cubo format. And the two formats are mathematically interchangeable and converted using this formula, where xi equals 1 minus sigma I by 2. So when formulating actual problems, cubo and 0, 1 is often easier to think about as compared to the icing spins, which makes cubo the standard model in quantum annealing, and it's used in many simulated annealing engines. And here you see simple conversion. Now the problem here is to minimize the sum of the numbers selected. Now there are three numbers, and you have to select the numbers in a way, select two numbers in a way that the sum of them is the least. So in this case, the variables can be defined by selecting box, but the xi is 1 if your box is selected, and xi is 0 if the box is not selected. So the objective function would be to minimize 17x1 plus 21x2 plus 19x3. And you will see whichever x becomes 0, only those two would be 1. That will provide the minimal result. Now, to do this, you create constraint expressions and you convert them to penalty functions. So in this case is the quadratic aspect coming in, where you say x1 plus x2 plus x3 has to be 2. That is your first constraint, because only two boxes have to be selected. And how do you represent this quadratically would be you bring the 2 to the left-hand side and you square it. On the cubo, what you do is you provide the objective function, which we've seen here, 17x1 plus 21x2 plus 19x3. And then you add the constraint, which is a quadratic representation of this constraint. Only two should be there. Where the idea is to also introduce a weight constant. Now, if this constraint is not satisfied, we would want this to be a large value. So that it adds to the final sum, and it will not be a minimum value, which is why we introduced this idea of a penalty function. But eventually what we want here is we want to see if there were multiple constraints, we would add a specific notion of penalty to them, so that you can decide which constraints need to be hard and which constraints are, let's say, you can work with them. So finally, solving the cubo, you will see that x1, x2, and x3 have their values, where 17 and 19 together will provide the least sum out of the three boxes. So a little about what NEC. So now that we have covered a little bit of the theory, we want to talk about the solution now, and we'll slowly approach towards the solution. But this is a little slide that talks about what NEC is doing. And on the left, you see annealing methods, and on the right, you see quantum gate-based methods, where you see organizations like IBM, Google, Rigetti. They have also been working towards creating quantum gate-based systems, and NEC is working on that as well. But as of today, we are working on quantum annealing and superconducting circuits. And these are all basically government-funded initiatives that all these companies have directions from the government on how to approach the quantum realm and provide effective solutions in that domain. This is a nice little bit of trivia about NEC, that it was NEC was the first company to demonstrate a solid-state qubit in operation, and that was published in the Nature magazine in 1999. And from then we have these dedicated quantum teams, and right now we are in this phase where vector annealing that we are studying right now has been properly productized. The machine is available, and between 2020 and 2021, we had partnered with D-Wave, and right now we have, D-Wave also does quantum annealing, and we do, and we find like niche for each problem on our sites. And moving on in the time, we will develop and basically release our own quantum computers as well. We're trying to solve social issues using quantum computing. So what this talks about is where all quantum annealing is applicable. So in case of matching and recommendation, in terms of the advertising domain or infrastructure. In the manufacturing domain, you see there is a lot of production planning required, many combinations lead it as an NP-hard problem, where parts need to be ordered. That is a specific schedule. In traffic and logistics, there are so many combinations and quantum annealing is one of the majorly growing technologies to solve logistics problems, such as crew shifts, delivery plans, load placements. So you can see an actual problem can be a combination of all three, where um, a company has to understand how the shifts are going to work today. Then what is the delivery plan for today? Which trucks and which cars and which vehicles need to proceed in which directions, including avoiding traffic times for a specific part of the city. And in a truck, how would you place the loads? All of these combined can be, these are individually NP hard problems in themselves, but in the real world, a combination of all of them is subject to annealing. In finance, there are loads and loads of numbers, and you need to you know uh, use them for detecting card fraud. Then there are portfolios that need optimization. There's risk calculation. And in drug discovery, there are screening procedures that need a lot of combinations. There are so many experiments and there are so many parameters that need to be searched. All of these are prospect use cases for quantum annealing. And in our case, we have already worked with some super banks and a lot of logistic companies, and we are providing a solution as opposed to various other annealing platforms, which may not be solving industry level problems, but are still helping resolve smaller, uh, laboratory level investigation and researches. So all of this is worked by vector annealing right now. Yeah, and what's relevant to this lecture is, again, what are the steps to solve a problem with an annealing machine? So here we talk about what the problem is. So you need a review of the entire process. So if you take a logistics issue where a company has to decide at what time which trucks should proceed in what direction based on what crew is available. So there needs to be a clear understanding of what the problem is, and you define the problem that you need to solve, and you model it. Till now we've spoken about the Cubo formulation, and you can understand this part. Like, you really truly understand the problem, you understand what the objective is, you understand what constraints there are, and constraints could be many, like hundreds of constraints, and with various complexities. And you have to identify what the bottleneck is, because the bottleneck will help you identify the definition of the problem, what needs to be minimized and what needs to be maximized. So it takes a proper review of the problem, and then you try to find the combinatorial aspect to that problem, so that you can design it in the way that we just discussed in the terms of an objective function and constraints. And then we need a formulation engineering here, where we identify how the model was made, you formulate it, and you create that mathematical function from it, and you um, throw it into the annealing machine to get the solutions. And you can consider this as an iterative process. If your annealing solution does provide you, uh, you know, the relevant problems to your solution, you can actually keep tuning and keep modifying, or keep introducing more complex constraints to get a more and more well-defined solution to your problem. So this is basically the mindset or the workflow that you need to solve that problem. Speaking specifically of the vector engine and the vector annealing, how does it help? So when we spoke about simulating the idea of annealing, you see that the energy matrix and the spin states are basically, when you try to simulate it onto the classical computer, you see that it is actually an example of a matrix vector product. So if you're performing a matrix vector product, you identify that HPC solutions, they will end up providing a good performance to these kind of computes, because that's what we see in various other HPC codes. The fact that vector annealing, simulated annealing, is also a form of matrix vector product, helps provide high performance to these matrix operations. So that's where the vectorization aspect of our of the vector engine helps. Then the other thing that is provided by this hardware is, as you see here on the left, is on the center is the vector processor. This vector processor has very large vector pipelines where each vector register is able to store 256 double precision elements, and there are 64 such registers on this card. So if you compare this with the AVX of Intel, then that has AVX2, I think, has 512 bits worth of vector extensions. So 512 of the CPUs compared to 32K, which is on this, and 64 of those. That provides a very good platform for these kind of computations. And these little chips that you see around the CPU are high bandwidth memory chips, HBM2 chips of 8 gigabytes each. So 6 chips of 8 gigabytes each provide 48 gigabytes on core in close proximity with the processor. So this essentially translates to really high memory bandwidths. And 48 gigabytes of memory on the classical hardware is capable of simulating up to 100,000 qubits per vector engine card. So using this 48 GB memory, we can work with problems dealing with up to 100,000 fully connected qubits, which is a large number compared to the solutions that are available, the annealing devices that are available today. And if you want to add more cards, then multiple cards are supported. And together, 8 cards can simulate up to 300,000 fully connected qubits. So when we say vector annealing, we are talking about annealing specific to the vector engine. And these are the features of the hardware that make this solution a very well performant or good solution for annealing like operations. And that's covered on the left side of the slide. And this is the hardware aspect to vector annealing. The software aspect to the vector annealing is represented on the right side. And let's say this blue curve here is the objective function that we have been discussing till now. In a typical process of annealing, it's basically exploration of the entire search landscape where you address each local minima, you traverse through it, and then you identify whether or not this local minima is a solution by seeing if the constraints are violated or not. So let's say if this was that similar TSP problem where this local minima was indeed a solution, but some constraint was being violated. In that case, the annealer would anyway traverse the path, but not identify it as a solution because of a constraint violation. What we have designed in the vector annealing software is that if there was a constraint violation, we can remove it or we can skip that constraint before the annealing process starts. So we provide subtle hints so that when this curve is sent to the annealer, the solution space does not consider these minimas by skipping them if they were constraint violations in the first place. For example, let's say I have to travel to a place uh, by a flight through air, and then I have a list of 100 cities of where I can travel, and let's say 10 out of those cities don't even have airports. So why should I even consider that city as a possible solution and then see that, oh, there is no airport, so it's not a solution for me, and proceed? So in this case, we are traversing through all the list of cities, identifying that there is a violation somewhere, not considering that as a solution and proceeding. So when it comes to vector annealing and what differentiates vector annealing from other solutions is that you have options that we call flip options. And if you use those flip options, you're able to identify some constraint violations before the annealer accepts the solution space, which increases the performance by many folds. The gray bars that you see here are just indicative of saying that these parts are not even sent to the annealer, or they are sent, but the annealer knows not to go through them. So we are not breaking the problem down in any way. We are providing subtle hints so that the search space reduces, and that provides a boost in performance. So that's the software aspect of vector annealing that provides an extra performance. So one good thing is that we are able to simulate a large number of qubits, and the other thing is that we are able to skip some constraints, thereby providing a really high performance to the entire annealing process. And this also gives us uh, the possibility to involve more and more complexity to your problem, thereby creating more room for creating more industry level or more real life constraints or problems to solve. Is qubit pair coupling in entanglement? Okay, and this is a very simple diagram of how the hardware looks. You just have a standard x86 server, and you install the vector engine on its PCI card. There are some OS and compilers and libraries. That is exactly what Texas A&M has provided us today. There are servers in their laboratories in their server rooms, and vector engines cards are installed on them. We will be logging into those and running some of our codes. So this is basically the setup that's required for vector annealing to work. So the solution stack is pretty clear from what I said. At the bottom is the SX Aurora Subasa system. That's the Linux x86 server. On top of that sits the vector annealing engine, and where you can use Python APIs as well as C++ APIs to call the vector annealing engine. And so going from top down, you can see you have a use case that might be shift planning or package delivery plan or integrated circuit, whatever your use case is, you formulate it, and then you use your formulation to convert it to Cubo. And the Cubo is provided to the Python API. The Python API speaks to the vector annealer. The vector annealer runs itself on the vector engine, and that's how you get the answer. So the input has to be Cubo. Problem size can be up to 300,000 qubits if you are using 8 cards, and the connection is full. And the algorithm is basically provided like in here. I have a question. Can we solve one problem on multi-cards, or should split the problem first? Dr. Shi, you do not have to split the problem. If you have one problem that uses up to 300,000 qubits, you can run them on multi-cards. Under the hood, within this vector annealer engine, for everybody who is well versed with HPC concepts, we are using MPI. We are using message passing interface to communicate between the cards together, and that is how we are able to retain the full connectivity. And that might also explain how one vector engine card is able to solve 100,000 qubits, but when you extend it to 8 cards, you go up to 300,000 qubits, because there is an overhead of parallelization under the hood using MPI. So your problem formulation does not care. It should not care if you're using multiple vector engine cards or a single card. I hope that answers your question. This is sort of a reiteration, but what you need to do is problem, then you formulate it. Cubo model, vector annealing, and result analysis, and this is iterative. Okay, now we go into a little more specific of what is step 1 and further. So the first step is to assign the number of spins And by number of spins, we can say variables to solve a combinatorial optimization problem. Then from the conditions for the optimal condition of combination of spins, you determine the equation that needs to be solved. So these are the manual processes. You have to do that. The user needs to have that amount of understanding of how to formulate it. But from your formulation to the cubo creation is automatic, because we have libraries that convert problems or those mathematical equations into cubo model. One such library is called PyCubo, which we will be using. So what we did a few slides ago was basically an understanding of how a cubo can be formulated, but there are tools to do that automatically. So when you have a real life problem that is very complicated, you do not have to work on that mathematically. These Python libraries are available to do that for you. And then once the cubo is created, you pass that on to the annealing API. And then, as you've already realized, annealing itself is also an automatic process. The only strength that as a programmer you can apply to it is at the formulation stage, where you can use the right parameters and the right formulation to have the most optimal solution. Beyond that, everything is automated. Spin assignment is pretty basic, and we've done that, where spin is 1 when the event has occurred, and spin is 0 is when the event did not occur. Okay, so now I think we can move towards the hands-on. I have a few slides that talk about the code before we go on to the code. So let's take the slides first.
Might I suggest that we take a short break?
Oh,
I'm
okay.
a little over an hour in. So how about a 5-minute break? Okay.
Absolutely, 5 minutes is good. Hello, everyone. Is my screen visible?
Yes. Well, we
Great.
see finding a problem and formulation.
Great. Yeah. So before we move into the coding aspect, let's see how we code. So here you can see that defining a problem using a binary or spin format. So let's take a problem that's number partitioning, where you have to divide given set of numbers in two sets, such that the sum of the elements of one set is equal to the other set. So you've been given 2, 4, and 6, and you have to break this set down in a way that the first subset, the sum of the first subset is equal to the sum of the second subset. So it's such a small problem that we can see that 2 plus 4 is equal to 6. So our intended solution would be a subset of 2, 4, and the other subset with 6. Now in this case, if the array element is taken, then the value is yes, is 1. And for subset 0, if x array element is 0. So the three binary qubits can be defined as 0, 1, and 2, x0, x1, and x2. The sum of 2 would be 2 times x0 plus 4 times x and this. And then we also see that the sum of subset 0, or we can call it S0, is 2 plus 4 plus 6 minus the sum of this. So now we have a pretty well-structured problem where we have one sum represented as binary qubits, and the other sum represented as utilizing the first sum. And in this case, the difference should be minimum or 0. So we also have an objective. Our objective is that sum of subset 1 and sum of subset 0, their difference should be 0, or basically minimum. So now we see that we have a cubo formulated, where when you make it quadratic, you will say a difference to the power 2, which is what you see here. This is your final cubo. And That is how we have been able to formulate our little number partitioning problem. How do we put it in code now? Cubo, we've already gone through it. It's created as a Hamiltonian expression. And in this case, this is how our cubo looks. And we use PyCubo, so we don't have to code for it. We will just call a PyCubo library, and we'll have our cubo in place. Okay, and then finally for the annealing step, we provide the cubo model to the annealing solver, and we need some parameters that we have to provide to the solver along with the cubo. One of them is called the number of reads. So number of reads actually stands for the number of initial samples per annealing. So by default, it's just one, and we usually keep it one, but it gives you a grasp on how many samples you want to use for the annealing. Number of sweeps is basically the number of iterations to run over the variables over and over again. So more sweeps will usually end up improving the solution unless you've already achieved the global minimum. So these are two parameters that you have to provide to the model along with the cubo. So you're providing a cubo and you're telling it how many times you have to read the samples as an input initially, and how many times are you expecting the annealer to perform the annealing sweep over and over onto that. And as we spoke about it, larger number of sweeps usually provide an improved solution. But you have to identify the right number of sweeps for your problem, because you may like there is a point where sweeps just may be redundant beyond a certain point. There are some advanced options which we are just introducing at this point. We don't have to bother much about them, but we've already spoken about those, so we can at least mention them. One is the flip options. You can provide those flip options right now, where you can have some fixed pins, or you can have some initialization options. I will go through these in the future in upcoming slides. Then there is the temperature range, or the beta parameter. When you have multiple constraints and you want the annealer to know which constraints are hard constraints that you just cannot escape those, your final solution needs to have that specific constraint met, then you will provide a specific temperature range for those parameters. And if there are other parameters which can be circumvented, even though it will not be the global minimum solution, but you end up telling against each parameter. So those are some advanced options. And then there is an option called vector mode. It's explained on the next slide. So these are how the parameter look. Number of reads, we've already went through them. It's an integer type parameter. The default is 1, and it's number of samplings. Number of results is basically the default is none, because if finally you would want one optimal solution where none or one is specified. Otherwise, if you want to increase that, it returns all the annealing results when the same value of num reads. For each num reads, it will provide you all the annealing results. This may be necessary at some points where you're trying to analyze your solution, but eventually when you're using it, you would want the most optimal solution. So the default is none, or you can specify one. Number of sweeps, as we spoke, the default value is 500, where if you don't specify number of sweeps, the annealer will go and repeat the operation 500 times to zero down on a more optimal solution. The beta range, as I discussed, so you can specify the start and end values. And in this case, the n steps that you provide is the number of divisions from start to end, and it's an optional parameter. Then you provide an initial spin. It is also an array where initial VA spin, you specify the state. And there is, sorry, it's not below, but we have a specific section about it in the user's guide. Vector mode is also important, where you can either set it to accuracy or you can set it to speed. So annealing is run in speed priority when it when you set the vector mode to speed. So in this case, the priority would not be the accuracy of the solution, but how quickly you can get a solution. And then if you provide accuracy as the input to vector mode, then it will spend a little more time on the annealing, but it will focus on the accuracy aspect, that your answer would be more accurate. And there is a constraint priority where you want the constraints to be the most like you don't want a very speedy output, but you're saying that all the constraints have to be prioritized. That is my priority. Whatever answer you give me should have the constraints met. So these are some options that are provided with the vector mode. Oh, and when you analyze the results, it has certain parameters that you have to look into. One is the spin, that's the output of the annealing. Then the energy value per solution. We've already discussed that the most optimal solution as per annealing would be with the low amount of energy. And the time to solution. And what you see here is the annealing landscape, and the number of sweeps is on the x-axis. So you see that the time to solution achieves a minimum point with a specific number of sweeps. And you can also find uh, a specific region beyond which the probability of success is 100%. And before that, the probability of success may not be 100%, but it'll be very close to success. So these are some analysis that you have to do with your final solution by checking what the time to solution was, because there is a point where a curve has an increment, but then you also have to identify this little wall. After that, if you keep increasing the number of sweeps, you will find that the probability of success is 100%, but the time to solution again monotonously increases uh, because the number of sweeps are not providing any value anymore. So this is how you have to find the result. And there are times when you will see that it's not up to your expectation. So you actually send it back to the annealer with some parameters modified. And that's how you figure your result out, which is a partially uh, manual process, if you may, even though the output generation and all the numbers would be provided by the annealer. So again, these things you see here, spin is represented here, where it'll provide you with the answers to how the annealer responded, what the energy value was for that solution, and how much time it took. So to just summarize all of that, this is how the Python code looks like. So you first import vector annealing, and then you formulate the problem. We already had the Hamiltonian, so we just say H equals the same thing from the previous slides. Then you create the Cubo model, where you call h.compile. That's how you send it to the PyCubo. And then you perform annealing once you have your Cubo and offset prepared. You create a variable called model. You call the vector annealing library, and the model accepts the Cubo and the offset. And then you invoke the sampler, which is vector annealing.sampler. Vector annealing, as you can see, is the name of the library. And finally, the results are stored as a outcome of the sample, where you provided the model that was created here to the annealer. You told it how many number of reads there are and how many number of sweeps there are. So with the basic inputs, without using any advanced parameters that we discussed in the previous couple of slides, this would invoke the annealer. And finally, to print the results, you just have to use this results array that was created here. And it has the spin energy and time within it. So the number partitioning problem can be written in Python like this. Cubo model creation, as we discussed, is also automated using a specific API. Any queries until this point? Great. Okay. Now we will slowly move towards the hands-on. We will look into the code, but before we look into the code, I am trying to explain how the code, what you will expect there. Now we have a traveling salesman problem. And the objective function of this traveling salesman problem is to minimize the distance between a pair of locations. And the constraints are we are not supposed to visit the same location more than twice. It's not more than once, it's more than twice. And not to visit two cities at the same time. So here you see how we create the Hamiltonian. It's a little mathematical, but I hope it gives a good enough idea. So the summation here, the first Hamiltonian that you create to the objective function is that 0.1 and 0.2. So we have to make sure that 0.1 is 0 and 0.2 is not 0.1. That is one of the constraints. The distance between 0.1 and 0.2 and the binary variable for that point in time and the next point. And the constraints can be defined by strength is basically the penalty function times the sum of the binary variable minus 1. So we're just making sure that the same place is not accessed more than once. So we're just trying to say that xij equals 1. So by bringing the 1 from right hand to the left, we create this quadratic equation. So by this we are saying that you cannot visit the same location more than twice, and not to visit two locations at the same time. It also looks very similar, but we're just talking about two locations through the binary representation of whether or not a place is visited. And the square. Finally, the cubo would be a summation of all these Hamiltonians, and it would be in the form of the Ising form. The question is, why is it more than twice? It's just a it's a change in, like, it can be a constraint. We're just changing it from our unusual understanding. We just don't want to same location more than twice. That may be because, like, one situation is if it's a salesman and he or let's say it's a package delivery system, and the first time there was nobody at the house, so they will get a second chance of visiting the same place on the same day to make sure that the package is delivered. So you can create an analogy like this, but we just identified this as a interesting constraint. Now, this is where we introduce some flip options. The first, for the sample code, the first constraint that we are including is a one hot constraint. The one hot constraint basically means that only one city becomes one at order I, and only one order becomes one at city j. So in this case, what you're saying is you're applying this constraint where you're making sure that only one variable can be one at a point. So if you have many possibilities, then one hot constraint literally means that there is one and only one possibility amongst all the possibilities at this point. So you go from the number of points, you loop through it, and you are representing two constraints using which you are able to specify that only one city becomes one, and at one point only at city j, the only one order becomes one. And then you create a second constraint, which is a fixed spin. So in this case, you define constraints on the fixed spin that when x00 is 1 and x of 0, which the second index could be any, while x first index could be any and at 0. So basically the row and this column has to be 0 in order to start from the city, which is j is equals 0. So to the VA model, you will just provide an extra flip option, which is one hot. So you have provided two constraints into the code, and finally sent those constraints into the vector annealing API along with the cubo and offset. There are other flip options as well, which need to be included in the Hamiltonian's formulation itself. So one hot constraint, what it means is that one of the spins is one in the entire specified group. So if you're specifying multiple one hot as a list, then you can specify the defined one hot in the variable one hot. You can send this entire list into which is a group of one hot constraints into this parameter. That's another way to specify this flip option. And similarly, when you have multiple fixed spin constraints, you can send the fixed spin list into the fixed variable into the VA model. Then there is another constraint that at least one of the spin states is 0 in the specified group. So in that, again, you provide these group of constraints, and then you send the and 0 flip option into the vector annealing API. So these are more like the user's guide to use the flip options, and there are about 8 flip options that we can talk about. But we will eventually move into the traveling salesman code. There is a question I didn't understand it. One hot is a penalty-like condition. It's a penalty-like condition. You can say it's a penalty-like condition, but it's basically a constraint where you can say that it's an exist. It's basically it's a flip option in our case. You're basically telling the annealer that out of all the spins provided, only one spin state is one. And just by saying that, you are making sure that in a case of traveling salesman problem, if you're visiting only one city, then it is a constraint that there should be no case where anything other than one spin is one. So this is your way of providing a constraint to the annealer that out of all the spins that you have input here, only one is possible. Only one it can be positive at this point. So this condition is known as a one hot, and it has in a way been templatized. So just by supplying the one hot, you're just making sure that the annealer understands that the constraint right now, it's pre-penalty, but it has to happen. Penalty like condition will arise when you're telling a specific constraints weightage to the annealer, that we will penalize the expression if this condition occurs, which is not favorable. So constraint and penalties basically they work together, and we are currently talking about a templatized kind of a constraint. I think we can move to the code so that things start making more sense now. Let's go back to the terminal. I hope everybody is able to access the portal. I will just do it again. So if we are all on this portal, we have to click shell access, and then you will be asked to log on. This will take us to the login node. From the login node, we have to SSH to the server called DSS. So at this point, is there anyone who's not able to do it? Looks good. And then we have to, let me increase the font size.
It might be those, yeah, three dots. There we go.
Finally. Because none of the keyboard shortcuts were working for me. Okay. So source VA setup is what you have to do to invoke the VA environment. I'll do so do we have the demo codes? So Lisa, is it good for me to proceed, or are we still seeing some problems?
So I believe that everyone that was able to log in with their access ID has been able to get onto the node. You're working from your scratch space, but you have everybody copying files to their home directory. So you just need to make sure that they're in the correct location before they can run.
Okay.
Type yes in the chat or be great.
This is the command that you have to run. And then I'll go to my home space and see. Oops. So we should be in the TSP directory. There's a Python subdirectory. And there you'll find the Python script and a TSP file, two TSP files. Okay, let me restart. So we go to clusters, we go to shell access. It takes you to the login node. So the first command that you run is ssh dss, which will take you to the DSS node. Are you able to come to this point, Dimitri? In the same node would mean in the DSS node? That's all right. Does it say at DSS? Great. Then the first command you have to run is source VA setup. So you'll be able to see this little prefix to your prompt once you're successfully able to do that. And then next command is the copy command, where you're bringing all the demo codes to your home directory. I've already executed this command, so I won't press enter. And you should be able to copy your codes. Great. Okay, so now let's immediately step into the code and see what it's doing. So now there are some functions, and I hope everybody is good with Python. This is a function that reads the TSP file. The input file is provided. You can see there are. Oh, I used VI editor. I said VI tsplib.py, and that's how I stepped into the code. And you can see along with the Python script, you can see two TSP files. These are basically, I got them off the internet. EIL51 is a set of 51 cities, which I will input to this TSP problem, that the traveling salesman has to travel to 51 cities. And then there's a slightly larger version, 101 cities, but we can skip that, or we can just do one of these. Doesn't make a difference to our understanding. So the first function here, what it's doing is it is reading the TSP file, and that's the input file. And other commands are just relevant to reading and assigning some variables. Then there is a function where the distance is being calculated between 2 points. So you provide point x1, y1, x2, y2. Those are the coordinates that we're getting from the TSP file. And then you just calculate the length, that's x1 minus x2 as a quadratic, plus y1 minus y2 as a quadratic. And your length would be the square root of length 2, which was just created. And finally, this function would be called point underscore length, that would calculate the length between 2 points that were read from the file. Then distance calculation between all points would be required at some point. So this is the logic to do that. And finally, what you return is the length, the minimum, and the maximum length. This dmin is actually the distance array of the closest cities you can see here. And maximum length is basically the longest distance. Now we are getting and checking the spins. So in this case, we iterate through all the points. And if we see from the sample array, this actually comes later at the point of result verification. So at this point, I will not go through this, but this is after the annealing has happened and we are analyzing the result, and we are printing error messages where a specific location was not visited, or you visited a specific location more than n times. And these are all situations which will not occur if the annealing process went well and all your constraints were met. So These error messages will actually help you to understand if the parameters that you chose with the objective function and the constraints were good enough to make sure that the annealer knew what constraints cannot be included. So in such a case, this function comes in handy. But let's see if we ever get these messages, because we have designed the problem accordingly. I think creating Hamiltonian is what we are most interested in, because here you're calculating the length and you're returning it between two positions. And this has got to do with how the format is in the TSP file. When you create the Hamiltonian, you're defining the spin. So now you have the Hamiltonian of the distance between 2 points. You say spin x, you create in the format turn, city. Then you set the combination of those points. And finally, the constraint, the Hamiltonian of the constraint would be HA. This is again from what we had seen on the slide. HAD was the objective function. Hamiltonian for D is the sum of the length between J and K minus the D min, which is the distance between the closest cities. And then the spin X, this is exactly the same Hamiltonian from the slide. So you can see how we created that Hamiltonian. And this part has to be manual, where your own mathematical knowledge will come into play. And similarly, you create the same Hamiltonian for the constraints. We had two constraints that one city need not be traversed more than twice, and the other one. Now, HAD plus HAA and HAB is the final Hamiltonian, which represents the objective and the constraints. And now you will have to convert them to the Cubo format. But before that, there are some constraint definitions, which I had screenshot onto the slides. You are creating your one hot constraint and you are storing it into the one hot variable. Then you are creating the fixed spin constraint and you are storing it into the fixed variable. And finally, to create the Hamiltonian, you call this function, which is create Hamiltonian, and you provided all the information which we provided up in the function before. And finally, we call Hamiltonian.compile to convert everything that we created in the Hamiltonian to a cubo. This is the PyCubo function. After this, we get our cubo and offset. We've seen these in the previous set of slides for the simpler problem of number partitioning. Now at this point, you have your cubo set, you are designing your model, and before the annealing process, you are adding the fixed constraint and one hot constraint as the flip option. So what this is going to do, and I explained in the slide that was dealing with flip option, that before annealing, you are telling the Hamiltonian which constraints will be violated eventually, so that the annealing process does not have to traverse those paths. And this will increase the performance, because in a typical case of annealing, when one hot and fixed constraints were not provided, the annealing would still have happened. The constraints would still have been found and the answer would still have come. But just by using these flip options, we are already telling the annealer where not to look. We are already telling it that there are some constraints. So only one spin can be won at the same time. So as soon as you find the spin, you can skip the rest. And then similarly, there is a fixed spin constraint. So the annealer will be smart enough to not look where it already has been hinted that a constraint exists. So you can see how this is an additional step to annealing, but it helps reduce the time that the annealer takes by many, many folds, because the annealer now knows where not to look. So without these flip options, the situation would have been same, but slightly slower and maybe lesser optimized. Just by adding these flip options, you can see that the model will be prepared, but pre-annealing, it tells the annealer where not to look. And this is the process. Once the model is created here, you provide it to the sampler. And now the sampler will start in the annealing process with 1 read and 1000 sweeps. 500 sweeps was default, but we've identified that 1000 sweeps would be a good, and we basically do this with a little bit of trial and error. We can try 10,000, we can try 5,000, and we might eventually realize that 1000 is where you get the most optimal time to solution. And finally, you check the result. That's energy and length. And finally, you print the result. And that's all that there is to this code. Very quickly, we'll run this code by saying Python, specify the name of the Python script, and specify which TSP file we wanted to read. So so this is going to solve the problem of traveling salesman for 51 cities using NEC's annealer. And I hope everybody is able to catch the command here, Python, and then the script and the input file. It takes a while. And in a few seconds, we will have solved a practically unsolvable problem. Okay. So the energy was calculated as 109, which was apparently the lowest energy for this solution. The length of the entire traversal was 457. And this is the path that was returned, that from 0th location, you go to the 26th, then to the 5th, then to 47. It actually depends on how the TSP file was designed. And here you have the path for the for the shortest path in some ways. You got a different solution. Sure, so yeah, if I run it many times, it will provide different solution. So that is where we have to do a little bit of tuning, but we can also see that the length of your trip was 456. Now see, I got a more optimized solution. So it's about tuning the parameters in a better way so that you start getting more, like you can have more sweeps. Instead of 1000, you can try 5000, and then you will see that multiple runs will start showing more similar solutions across the board. Yeah, now the length is 445 in both, 449 and 445. Awesome. Next is a very interesting example. That's of the Sudoku game. Sudoku has been a very well-known problem for a long time. It's an NP-hard problem. It's a very difficult problem to solve on a classical computer. There is a lot of prediction that you need if you want to solve it using classical computers. But only the idea of traversing all possible outcomes of this solution makes it an NP-hard problem and a combinatorial optimization problem. A little bit about what Sudoku is, I think everybody knows, but in terms of objectives and constraints, let's just reiterate. The objective is to have one unique number in each box of the matrix, and to minimize the repetition. That is the objective, that the repetition should be minimum. And the rules, or in our language or context, the constraints would be that numbers 1 to 9 do not overlap in a horizontal row. The numbers that do not overlap in a vertical column, and within a 3x3 square. So these are the three constraints that we have. And then we can also play with the difficulty level depending upon the hints and numbers to be guessed. But right now we have picked up an example from the internet. And what does the objective function look like? Now there are 9 cross 9 cells where each cell can take number from 1 to 9, making it a 9 cross 9 cross 9, which is a 729 cells total that can be expressed in either 0 or 1 to represent each number which will fill into the solution space. So here I is the row number from 1 to 9, j is the column number from 1 to 9, and then k is the number of each cell. This is the cell. So k would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have I, j, and k that represent. And now we have to say that each x, that's I, j, k, it can either have a value 0 or 1. This is how we can formulate our objective. Then from the rules, we can consider 5 constraints. First constraint is that a single cell can have only one number. Now that was very obvious, but to, to put it as a constraint would help us get a solution. So the summation from 1 through 9, where xijk can only be 1, that's the first constraint. The second constraint is that each column cannot have a duplicate number. Now this was part of the rules. So here we again say that for each ijk, the xijk has to be 1, because that's the cubo representation. Then again for the row I, what was for the column is the same for the row. And again for here the summation is through j. You will see that that is the third constraint. The fourth constraint is each of the 9 3 cross 3 subgrids cannot have a duplicate number, also part of the rule, but we represented it slightly differently. Here we have a summation of the I and j so that you can pick a specific 3 cross 3 subgrid. And for that, again, it equals 1. And the last constraint is initial numbers that is given as hint cannot be changed. So 8, 5, 1, 1, 8, all the numbers that you can see, which are the hints to the puzzle, they cannot acquire a different number. That is also a constraint. Like we don't want the annealer to replace this 8 by something else and eventually cause confusion. So this is a fifth and one of the most important constraints, that the hints have to be treated as hints and not to be replaced. Okay, let's go back to the prompt and look at the Sudoku code. The Sudoku code is also available in the same subdirectory where the TSP was. So we just go to Sudoku Python, and here you will only see one file because we don't require any TSP file. So I use the VI editor again for, yeah, now we are inside the code. Similarly, let's do a quick walkthrough of the code. There are some helper functions here. The helper functions are letting us know that we are checking the numbers, and we are iterating over the entire grid here. And we are saying, oh, before everything, let me go down and show you. Yeah, this is how we have the initial setting that we saw on the slide. We just created a grid, and you can see everything is a 0 that needs to be guessed, but all other numbers have been filled with what hints are provided with the initial set. So in this case, you will see that there is a initial setting, and you can identify the hints. Now there are some definitions here where columns, rows, and numbers are 9. I just wanted you to see this. We are slightly deep down into the code, but now that we've seen that there is a hint matrix that exists, I will take us back up where we started. So here, now we know how this matrix looks like. And in this case, we check horizontal columns and the index of 9 cross 9. So Let's see what numbers is. Oh, sorry. So numbers is 9, as you can see here on 253. Rows is 9 and columns is 9. Let's go back. So what it's doing is it's iterating from 1 through 9, and it is checking if any value is 1, or if the hints matrix shows that it's not 0. So this is basically where you're identifying if what you have been provided with is error-free. Then you do a horizontal check. You do the same thing again, and you raise an error if there is a problem with the horizontal check. Then you do a vertical check, and you raise a problem or an error if there is a problem with the vertical columns. And then you check the same thing within 3x3, and you raise an error. This is not relevant to the annealing process. We are just making sure that our initial 3x3 matrix is uh, uh, as per the rules and ready to be solved. Now, this is what we're doing. We're calling all of these check number, check vertical, check horizontal, and everything before we start selecting the numbers. And in this case, again, you are selecting those numbers which are to be solved. This is just a print function which helps print the matrix later, so not very important. This is where we create the first Hamiltonian. So we define the spin where we say cubo x is based on 9 cross 9 cross 9, and the numbers can be binary. The first Hamiltonian is about the first that there must be one number from 1 to 9 in one cell. That's the first constraint. So we use cubo x that we created up there, and based on that we added to the HA1. Then we created the second constraint where we are talking about horizontal row should have unique numbers. And similarly, we create all 5 Hamiltonians using the math that we understand. And finally, the create Hamiltonian function returns sum of all 5 Hamiltonians. Now you see here, we have assigned a penalty to the 5th Hamiltonian. We are saying that keeping the hint number is the highest priority. You cannot mess with that. So if this becomes anything, then your solution will be penalized and automatically pushed to the back, that it won't be identified as a good solution if any of the combinations lead to modifying the numbers for the hint. So this is our first example of penalizing a specific constraint. Then we are also working with the one hot constraint, because at a point there can only be one spin possible. It will help us optimize the annealing process. So we are creating one hot constraint for each number. Then we are creating a one hot constraint for each column. Then we are creating the same for each row and for each subblock. And finally, the sum of it is, or the combination of all are being saved to the one hot, which we will provide as a flip option. Similarly, we are creating a fixed spin constraint as we did in the TSP problem, and eventually making sure that the annealer knows that there would be fixed spins. Then upon creating the model, we create the Hamiltonian. We just went through this function using which we use the PyCubo to create the cubo for the Hamiltonian that we created. We specified the one hot constraint and the fixed constraint. And while initializing the annealing model, we give it the cubo, we give it the offset, and we give it all the constraints that it has to look for before annealing. And finally, the annealing process happens where you create the model, which we have already seen up. The sampler is initialized, and the sampler now reads it 5 times. The sweeps are 200. And here you see we have introduced a new parameter, which is num threads. So we can also multi-thread this problem. Vector Engine has 8 cores. So we are utilizing this advanced option of multi-threading, where multiple threads can help optimize the problem further. And finally, for checking result, we see whether a constraint is broken or not. And we see what the energy value came out with the final solution. Having read through this code, let's run it very simply. Python and the name of the script, and enter. So this was the hint matrix, and that is a solution. A practically unsolvable solution, unsolvable problem for classical computing was solved in a matter of a second or two by using quantum annealing. So this is the strength of annealing. We can do it as many times. Right now, the hint matrix is hard-coded, so you will always get the same solution. But you can see that how the annealer, just by providing it a simple set of rules as constraints using basic linear algebra, we have been able to automate the entire process of taking a combinatorial problem and solving it through simulating the idea of what may be happening at the quantum level in a material. So you can try this out. You have access to all these codes. You can play around with the hint matrix. You can use your knowledge of Python and create a dynamic hint matrix where, you know, what the problem may look like or what the puzzle looks like can be stored dynamically, and then you will see that in a matter of seconds, the quantum annealer will be able to solve this Sudoku problem. And it's a wonderful exercise to play around with these numbers. You can try more grids. You can increase the size of the Sudoku problem. You can add your own rules, and you will see that as many combinations as there are, the annealer will be able to process through them and come up with an answer. There are many solutions and many sample codes available. Um, we'll run, the annealer can solve all those problems. And yeah, thank you, Dr. Shi. You have provided a little hint to everybody that the student has ran 49 square quantum annealing Sudoku. And on vector annealer, I'm pretty sure because we have a larger landscape and a larger set of qubits that you can play around with, I'm sure you can try to run something on these lines with a larger set, maybe more than 49 square. So what we are seeing here is just 9 square, but using this quantum annealing, we can, I think there's no limit. The limit is only the hardware limitation right now. But it's great that this new technology has come about, where by imagining how particles would react at a quantum level and simulating those reactions within the classical realm, you can use the classical computers to solve such problems. We are very close to completion of our tutorial today. And I believe, given the theoretical and the hands-on experience, we are at a good point right now. There are a few more slides that explain some other use cases, which are slightly more complicated. Let me take you through this one quickly. This is a combination of a traveling salesman problem as well as a knapsack problem, which I think every courier company has to deal with. You can see there is a constraint on how the traveling salesman or how each destination has to be visited. But at the same time, before the truck starts, there is a way in which you want to arrange the boxes within the truck, so that it complies with your plan, your delivery plan. It should not be like the first location needs this box, just to access which you have to take all the boxes out. So this is a knapsack problem where you're trying to find the most value of an arrangement within a specific bag added to the traveling salesman problem. But you can simply see these as more constraints. So in this case, one constraint is a loading restriction, where you're saying that the truck can only have 18 boxes in 3 rows of 6. And you're saying that 15 delivery locations per day. And there has to be some free space in the cargo bed to move the boxes around. And you cannot have the heavier boxes tagged onto the lighter boxes. And you have created like 3 criteria. So in this case, again, there is another code in the same directory, LLRO. LLRO stands for Load Limited Route Optimization. So I would have gone through that code as well, but I believe it's just, an extension of what we have already understood. And with this, I would like to invite everybody to try out the LLRO code. You have access to these slides. You can understand how the Hamiltonian was created for each one of them. So the function, the objective function has several parameters to it that, the distance, and then minimize the distance of the delivery route was considered as one Hamiltonian. And then the remaining constraints were also treated as Hamiltonians. Another added constraint was the way the boxes are arranged in there. You have to penalize some of them where, it's the heavier boxes on top, and so on. And when you finally have all these 4 constraints, you can add more penalty based on which ones you want, which constraints you want the most to be penalized versus which ones you're okay with. And finally, we can look at the LRO code. I encourage everybody and invite everybody to look at this code yourself and try running it. Well, and there's some benchmarking approaches which I wanted to talk about, but again, I think with the knowledge that we have, I believe it's a good point to stop. And I'm very happy to receive any questions and queries from you guys right now, or maybe offline. I'll be sharing my contact details with everybody. And if you need any help in formulating a problem or using the vector annealer, you can also reach out to me for that. I'll be very happy to support you guys. That's my email address in the chat. And with that, I'd like to thank everybody for your time.
Thank you so much. That was wonderful. So open the floor for questions, and give a big thanks also for providing your contact information and your willingness to support development. So there's a question in chat.
How should I access to these resources? I believe Lisa, I think you already have access to these resources on the ACES cluster.
Yes, if you want continued access, I will be sending out a message about continued access for the vector annealing component of the NEC vector engines.
Louis, you are raising your hand.
Yeah. First of all, thank you for the presentations. It has been amazing. I am taking a look to the PDF. It has many other information. Thank you for that. What happened, or what should I do if I would like to use, for example, or to try or to test all the PBA, populated based algorithms, for example, PSO or genetic algorithms? Because you showed some problems, and I would like to test with others solutions, right? Because in evolutionary computation, for example, that is my focus, or not my focus, but it's my expertise. I would like to test how the GA works with in comparison with simulated annealing, for example, or VA better. So what should I do?
That's a deep question, because they're completely different technologies.
Yeah.
You have to formulate the same thing which you've been using your analytics for. you have to rethink on those lines, and you have to again form a basic linear algebra equation, use PyCubo, but you have to identify what your analytics are, what's the objective of those, what is the final objective. So create an objective function, then think of some constraints which you need met, and you just have to reformulate those problems in a different way. And for genetics, we have seen some open source databases which you can access, where this is already like Cubo friendly. So if there is a specific problem that you are working on, it may be a nice idea to check like open databases where similar genetic information, for example, in the TSP code, you saw I used a .tsp file. It was nothing but a free file from the internet, which had coordinates of 51 cities, 100 cities, 200 cities. And I just used that to first read it and store it into variables, which I can, eventually convert to QBOs. So similarly, you can get some genetic information. You may already have some data sets, but it would just be an act of rethinking those problems so that you can work with quantum annealing.
Perfect. Thank you, Raghu.
It's my pleasure. Dr. Shi, you've posted a message about how does VA compare to other digital annealing. A part of this has been answered in some of the slides where I introduced how the VA on the hardware side looks like and how its software component looks like. So one difference or one comparison that you can draw here is, first is that this is a classical solution to a quantum annealer, while digital annealers are based on actual QPUs. And because of this basic difference, we are able to, in today's date and time, we are able to leverage the power of classical computing and extrapolate or scale problems up to large number of qubits, while the digital annealers are using quantum technology or superconductivity, and they are limited in size with number of qubits. So it becomes a case of comparing a problem that uses, let's say, a few hundred qubits that can fit on a digital annealer, or a few thousand qubits that can fit on a digital annealer, with the same size of a problem run on vector annealer. And in some of our internal benchmarks, we've seen that the performance difference is not very different. If you run a small problem on, let's say, an existing digital annealer, and you run the same problem on vector annealer, you will probably see the performance and the energy values be kind of similar. You won't find a large difference. But the true power of vector annealing is unleashed when you introduce more complexities, real life constraints, and you increase or blow the problem up into something that's more realistic. Like we saw the load limited route optimization, where how to fill the truck is also a constraint, then how the truck has to move into the city is also a constraint, and then traffic jams and crew shifts and all of those things. They would basically result in more realistic answers, more relevant answers to the industry. And the 100,000 and 300,000 qubits that we are working on are also fully connected, which means each qubit can interact with the other qubit, which is not the case. And you're right, and you've mentioned that QA qubits are not completely connected. Yes, 8 cards fully connected, 300,000 qubits. Oh, is what? So you're saying, yeah, 300,000 qubits. Is your question 8 cards fully connected 300,000 qubits equals 8 into 100K? So got it. Yeah, 300 is coming more from our experimentations. 300 is the practical value. And when I mentioned that under the hood, we are using MPI, message passing interface, to communicate between one vector engine card to the other vector engine card. So the overhead taken up by MPI and the message passing is to the extent that the number of qubits when you scale up from 1 card to 8 does not grow linearly. A lot of time is taken up by the MPI, which is why we are able to accommodate only 300,000 qubits on 8 cards. It's majorly because of the MPI overhead.